matrix representation of linear operator. This will correspond to what we talked about in 4.5. With their matrix representation, we will see that linear operators on vector spaces can be studied in much the same way as linear operators on Rn, and that will be very convenient, as we will see. First, let's go over matrix representation for a linear operator on Rn. Suppose T is a linear operator on Rn, and then we have a basis for Rn. Then the matrix representation of T with respect to the basis is defined as a matrix like this. The first column vector is the image of B1. And the second column vector of this matrix is the coordinate of the image B2 all the way to the coordinate vector of the image of Bn. Then, if we want to compute the coordinate vector of an image, it can simply be computed like this. Is the matrix vector product. The matrix is the matrix representation of T, and the vector is the coordinate vector of V. And we have derived a number of results about matrix representation. For example, T is invertible if and only if its matrix representation is invertible. For vector spaces, a matrix representation is all the more convenient. Why? Because it's a matrix, and we have derived so many properties about matrices. If we can have a matrix representation of a linear operator on a vector space, we can then use what we have learned about matrices to study the linear operator. So how can we have a matrix representation for a linear operator on a vector space? Suppose T is a linear operator on a vector space V, and B is a basis for V. T goes from V to TV. This is T. To consider matrix representation of T, let's consider the coordinate vector of V and TV. From TV, we can obtain its coordinate vector by applying phi b. Then we get its coordinate vector. And now if we want to get from the coordinate vector to V, that will be the inverse of phi b. Now let's consider the composition of phi b inverse, T, and phi b. So it goes from here to here. U from Rn to Rn is the composition of phi b, this one, and then T, this one, and then phi b here. What kind of function is U? Is U a linear operator on Rn? It goes from Rn to Rn, right? Would it be a linear operator? Well, it is the composition of 3 linear transformation. So U is indeed a linear operator on Rn. Well, if it's a linear operator on Rn to Rn, then you would have a standard matrix, right? What is the standard matrix of U? If C is a standard matrix of U, how can we obtain C? And it's a linear operator on our end, so we know the standard matrix consists of images of the standard vectors. In particular, the ith column vector of the standard matrix is the image of the ith vector, the ith standard vector of Rn. So let's plug that in. U is phi bt, phi b inverse, and then ei. So let's first consider the image of the ith standard vector under phi b inverse. Phi b inverse goes from Rn to the vector space V, and then if we have ei here, that means the coordinate vector is the ith standard vector. So the vector itself would be all 0 except the ith vector. For the ith vector, we have coefficient equal to 1, and all the others are 0. So what is the image of ei under phi b inverse? It will simply be bi. So this is tbi. And then we apply the coordinate transformation. So we get the coordinate of tbi. Putting all the column vectors together, we have the standard matrix of U, the C matrix. The C matrix has column vectors equal to the coordinate of the image of the ith basis vector. This C matrix is called the matrix representation of T with respect to the basis B, and it's denoted by TB. The U linear transformation has a standard matrix equal to C, so we can view U as a linear transformation induced by the matrix C. If we go back to this picture again, then we can have the composition of the three equivalent to this one. This is U, and U is equal to TC. And this is C matrix is the matrix representation of T. So now when we look at the image of TV, the coordinate vector of TV, we would have U, that is the same as U, the coordinate vector of V with respect to B, and this will be the image of this vector, this coordinate vector under U, and that's the same as the matrix vector product CVB. And that's the result of theorem 7.10. For the case of Rn, we mentioned that the linear operator on Rn is invertible if and only if its matrix representation is invertible. Now let's see if this is also true for a vector space. Suppose T is invertible. Now the question is the matrix representation, the matrix is invertible? And or we can say is U invertible? This U function is invertible because we know for Rn, U is invertible if and only if its standard matrix is invertible. And we look at U, which is the composition of the three linear transformation. if T is invertible, and these two are already invertible, then U would be the composition of 3 invertible linear transformation. Does this mean U is invertible as well? Yes, it does. Now the converse. If U is invertible, so its standard matrix or the matrix representation of T is invertible, does this mean T is invertible? Well, this is how U is related to T, right? So let's see how we can relate T to U. We can, for example, we can have one more, phi b, and phi b here. And we can have phi b inverse here, and phi b inverse here. Then we see that these two will cancel off, and these two cancel off as well. And we get T equal to this composition. If U is invertible, then T would also be invertible as well. So the converse is also true. And we get the conclusion, T is invertible if and only if its matrix representation is invertible, just like the case of Rn. An example. Suppose T is a linear transformation and linear operator on M2 by 2, and it's defined by this. T of A is equal to A transpose. And we know this is a basis for M2 by 2. Let's find the matrix representation of T with respect to the spaces. So the first vector in the matrix representation, the first column vector, is the coordinate vector of TB1. If we plug in B1 here, the transpose of this matrix will be itself again. So we get B1 again. This is the same as B1 again. So the coordinate vector of B1, we get E1. And the second column vector of the matrix representation, C2, coordinate vector of TB2. This is B2, we plug it in. The transpose of this matrix is this one. And if we consider the matrix representation, the coordinate, then we get E3. Similarly, C3, the third column vector of TB, would be the coordinate vector of TB3. And TB3, this is TB3. And T takes transpose. So the transpose of this matrix is this one goes here, one goes here. And the coordinate vector of this matrix would be E2. The last column vector C4 is the coordinate vector of TB4. This is B4. The transpose of this matrix is still itself. And the coordinate vector would be E4. And putting these column vectors together, we get the matrix representation. The first one is E1, the second one E3, third one E2, and the last one E4.